Welcome back to EC 3030. Before today's lecture, we have two announcements on the canvas. So first, the homework 4 was posted, and it will be due October 23rd. I think that's a Friday, before the midnight. The next Tuesday's class, we will have no technical discussions. Instead, we will invite the ECE Advising Office to introduce the new protein engineering degree requirements and opportunities. So please join the Sam Blue Jeans link. You can ask the officers any questions regarding your curriculum or the degree requirements. And then another announcement on the second midterm. So this will be similar as the first midterm. We will have this 24 hours take-home exam, and it will be October 29th. I think that's 2 weeks from now. So we will post the questions on the Thursday, 12 p.m. And then you will need to upload your solutions before Friday's noon. So the midterm 2 covers the lecture materials from 9 to 14 only. So that means it's after the first midterm and before today's lecture. That means MOSFET IV, subthreshold current, and the CMOS inverters. So we will post the practice exam materials, and you will have opportunity to review the exam. I think that was from the last spring semester. And then we will have an in-person session to go over the solutions of this practice exam on next Thursday, and part of the class will be invited. And then we will have a virtual review session of the key concepts and the equations on the October 27th. That's the week after. So any questions regarding the logistics here? Okay, then we can start today's discussion. So today will be lecture 15. And we are going to discuss the CMOS scaling. This is a recorded lecture from last spring and also from Professor Asif Khan. So here we don't have the reference chapter from the textbook because the topics today are not in the typical standard textbook, because the scaling is more industry relevant and it's a topic that I think is important. So we have normally in the textbook you may have, there's no discussions on this one. I think it's important for you to understand the history of the microelectronics industry and how the industry scale the technology from micrometer scale to today's nanometer scale. Alright, so this is a MOSFET scaling, and this is a historical trend from 1970s to today. So a few decades ago, the transistor key dimension, here we use the gate length L to represent the key feature size of the transistor. And then it started from like micrometer scale to today's 10 nanometer scale. So here this is the 0.01 micrometer, so that is about 10 nanometer. So this is an exponential scaling trend. This is an exponential trend because this is log scale. And those numbers are the representative numbers for the technology load. And you may have 3 micrometer load, 2 micrometer load. To more recently, we have this 0.18 micrometer, or sometimes people call 180 nanometer, or this 0.13 micrometer. That is 130 nanometer, and then it's 90 nanometer, 65 nanometer, and 45 actually, and then 32, and so on. So this is the historical trend, and if we want to visualize the dimensions, for example, here, back in the 3 micrometer load, we have this transistor like this in this size. So we have the gate, oxide, and source and drain. But if we want to scale the transistor to today's like 14 nanometer load, then it will be something like this small if you want to draw this proportional to the dimension scaling. So it will become very small. But actually here the transistor structure also change. So here this is what we have learned so far in this course. This is the typical planar structure for the MOSFET. But today's transistor MOSFET use a different structure that is called FinFET. And we're going to have more discussions on the advanced technologies like FinFET at the very end of the semester. That will be in lecture 20. So we're going to discuss those innovations in the past few years to enable this scaling. But here we only care about the dimensions, and like the L, then we see this historical trend. So any questions? Alright, then let's look at the scaling. And you may have heard of the Moore's law. And we also discussed Moore's law at the very beginning of the semester. So basically, it's an observation that the number of transistors in a dense integrated circuit, like the microprocessor, doubles approximately every 2 years. In other words, the size of the transistor will be scaled about 0.7x from generation to generation. So the size is like one side, like the L or the W of the transistor. Then it's 0.7x. Then the area of the transistor will be 0.5x. So size like 0.7, then the area will be 0.5x from generation to generation. The reason is that if the side like 0.7 by 0.7, then the area will become 0.5x. 0.7 by 0.7 is 0.49, so it's roughly 0.5x from generation to generation. So this was predicted by Gordon Moore in the 1960s. And he predicted the number of transistors in the microprocessor doubles every generation. And it took about 2 years to evolve from one generation to the next. So here, this is an article from Gordon Moore to look back the history of this scaling. So if you are interested, you can read this article by Gordon Moore. But today we are going to discuss a different scaling rule that is called the Dana scaling. So the Dana scaling rule actually is based on the Moore's scaling. But Morse scaling only talks about the number of transistors on the microprocessor chip, or in other words, only talk about the dimensions of the transistor get smaller. Here, the data scaling law is going to discuss the metrics beyond the number of transistors. That means we are going to discuss the power density and the clock frequency. So how would those parameters change from generation to generation? So this is the topic of today's lecture about the standard scaling rule. It is based on the Morse scaling, but in addition, we are going to talk about how the performance, like the clock frequency, change from generation to generation, and how would the power density change from generation to generation. So this is the topic of the standard scaling rule. So Dennard, full name is Robert Dennard. He was an employee of IBM, and back in 1974, he wrote this famous paper and proposed this Dennard scaling rule to predict how would the power density and the clock frequency change from generation to generation. And the Moore's law, I would say, is more like economics driven. So Gordon Moore is the co-founder of Intel, and this is the transistor count of the microprocessor from generation to generation, and we do see this kind of exponential increase, and the transistor count doubles almost every 2 years till recently. But if you read the newspaper, there are discussions like Moore's law is slowing down, Moore's law is dead. So those statements, I believe, are partially true in the recent 5 years, as we see the Moore's law slows down. But still, the number of transistors from the generation to generation still doubles. But the pace slows down. So previously, it doubles approximately every 2 years. But in the past 4 or 5 years, maybe the generation to generation will take 2.5 years or even 3 years. So the pace slows down, but the trend is still ongoing. This is because we are going to face many scaling challenges, and we will discuss those challenges later in the lecture. Some of the parameters cannot be scaled, so the industry is facing the grand challenges ahead. And then here are more articles regarding the Moore's law. Yeah, if you are interested, you can read them. And here is the Gordon Moore's interview about the Moore's law. And this is Robert Dennard. He was the employee of IBM, and actually he is an IBM fellow. He not only proposed this Dennard scaling rule, but also he was the inventor of the DRAM process. So DRAM is the topic we are going to discuss later in lecture, I think it's lecture 17 or 18, lecture 18. So DRAM is used today in all the electronics here, like your laptop, smartphone. You have this 8 GB, 16 GB RAM, and that is DRAM. So he was the inventor of the DRAM as well. So here is another article regarding the Dennard scaling rule. And the Dennard scaling rule is more physics driven. Why is that? The reason for the Moore's law, or let's say the driving force behind the Moore's law, is more economics. The reason is that it only cares about the number of transistors on the chip or on this wafer. The reason is that if you scale each transistor smaller, then you can pack more transistor on the same wafer. Then the cost per transistor will get reduced. That's why those processors becomes cheaper and cheaper. The memory in storage like USB or SSD get cheaper and cheaper these days, because you scale the transistor size. You still pay the same cost to fabricate this wafer, but you can have more transistors on this chip, on this wafer, then you will have less cost per transistor. So that is the motivation behind the Moore's law. So Moore's law only talk about the dimension scaling, and it's cost driven. And here the Dennard scaling is more physics driven, and we will say that by doing the scaling, not only you reduce the cost, but the circuit performance will improve. And for example, the delay and the clock frequency can be improved. And we are going to discuss in more details in the next few slides. That was predicted by the Dennard scaling. Any questions here? All right. So what Dennard scaling suggests? So here, if we still use the Moore's law assumptions, like the transistor dimensions are scaled by 0.7x, that means reduced by 30%, or reduced to 0.7, 70%, let's say 0.7x, every technology generation. Thus the transistor's area reduced by 50%. This is still the Moore's law. And with the Moore's law's assumption, then we can further reach the conclusions below, that is the Dennard scaling, which states that the delay is also reduced to 0.7x. Therefore, we can operate the processor with higher frequency, about 40%. So it can be 1.4 times of the frequency than the previous generation. And finally, to keep the electric field constant, for example, the electric field within the transistor structure, then the voltage needs to be reduced to 0.7x, or by 30%. As a result, the energy will be reduced by 65%, and the power will be reduced by 50% at each transistor level. So this is regarding the power and energy. As a result, in every technology generation, the transistor density doubles. Transistor density, that means the number of transistors on the same chip area. Circuit becomes 40% faster because of the clock frequency, while the power density stays the same. So power density is defined as the total power divided by the chip area. That will stay the same. This is because the transistor's area reduced by 50%, and each transistor's power also reduced by 50%. So you have less area and less power. Then the power density, which is the power divided by area, will stay the same. So then this is the Dennard scaling conclusions. And in the next few slides, we are going to derive those numbers through some practice. So before that, this is the original paper from the Dennard. So then if you are interested, you can read the original paper. But we are going to use the same approach in the original paper to do the derivation in the next. So here, let's assume, okay, the nth generation and the n plus generation, the dimension parameters, like the TOX, that is the oxide thickness, and W, that is the width of the transistor, and L is the length of the gates. So those dimensions will reduce by X. So all the dimensions reduced by X. And this is a scaling factor, X. At the same time, the voltage, like the power supply VDD, and the threshold voltage VT will reduce by X. As a result, the field is constant. Why? So here are the dimensions. And here we have the voltage. So you know the electric field is a constant in this case. Because you use the voltage divided by dimension, then you get the field. Voltage scale by X, dimension scale by X, field is a constant. One more assumption is that the doping density needs to be increased by X. So here the NA and ND are the doping density for the NMOS and PMOS. So here are the assumptions, and then next, let's derive the Dennard scaling rule. So the total area of the microprocessor chip is A, and then the area of a single transistor is W times L. Of course, it's proportional to W times L. It's larger than that, but it's proportional. So if you think about the transistor, single transistor, W times L actually is the gate area. But of course, you have some contact area for the source and drain. But overall, this area is proportional to the W, the width. And then this is like a single transistor's area. So the number of transistors on the total chip is just A divided by the single transistor's area. So this N is the number of the transistors in total. And the area of the next generation of a single transistor will be scaled by X squared, because W become W over X, L become L over X. So the area of single transistor scaled by X squared. Then the number of transistor, if we assume the total chip area is a constant, total chip area is a constant.
Hi, Professor. Excuse me.
Yes.
I think your PPT is very delayed. We cannot see your actual drawing.
It's delayed?
Right now, I can't see the PPT either. It's just completely black screen for me.
It's frozen.
So how about now? So can you see the screens are flipping? The slides? No?
We can see the Dennard scaling now.
So let me stop sharing and redo the sharing.
Sure.